Let me now discuss multi-d-instanton contribution. So last time I discussed the one instanton contribution in Z equals one string theory of this ZZ elementary ZZ type. And I consider the leading contribution and the first subleading contribution as expansion in G string. Now let's consider two instantons. Consider a pair of ZZ instantons. These are still of the elementary type, the 1,1 type that I defined before. These will be localized in time. So let's say at x1, 0 and x2, 0. These instantons, with two ZZ instantons, they have two moduli. You might expect that there's an integration over the moduli space, which is parameterized by these two coordinates of the ZZ instantons. So it will be dx1, let's call it, dx1, 0, dx2, 0, the time coordinate. Now, if you think about the diagrams that would contribute, at G string to the 0th order, there's a new type diagrams that will contribute now, which is the Annulus diagram. In fact, there would have been Annulus also in this case of one instanton, but the Annulus diagram is first of all divergent, and we can regularize it. And one way to think about it is the diagram can be absorbed into the normalization of the instanton measure. In fact, Ashok Sen has given a more careful discussion of that from the perspective of string field theory. However, if you have two instantons, then you have the exponentiation of this Annulus diagram with the, actually, let me move this down here a little bit. With one boundary ending on the one instanton and the other boundary ending on the other instanton. Oh, whoops, I'm going to use a different color. 1 and 2 here. So the worldsheet is this Annulus in between. Okay, so I'm using red to label the first guy, and blue to label the second instanton. The factor 2 is because the orientation. So there's not a diagram with the 1 and 2 exchanged. This diagram is now going to depend non-trivially on the position, on the coordinates of relative coordinates of x1 and x2. So it's going to give a correction to the instanton moduli space measure and order G string to the 0th power. Okay, so even if you're doing perturbation theory, you have to take this into account. I mean, doing the instanton perturbation theory, you have to take this into account. And then some appropriate diagram with closure insertions. So it's interesting to inspect what this diagram looks like. So let's calculate this guy. This diagram with the Annulus 2 and 1, this is easy to calculate. This is just the cylinder partition function. We have to remember that you have the ZZ boundary condition for the Liouville part for both boundaries. But this is fairly easy to calculate as a cylinder partition function. So you have the integration of the cylinder modulus T over 2T, which is the volume of the conformal Killing group, as in any kind of open string one-loop computation. And then we've got the worldsheet theory involves tensor product, the three parts: Liouville, the time-like boson, and the BC ghosts. So the Liouville partition function, remember, it's just a vacuum character, as I discussed last time. So this is just give you e to the 2 pi t minus 1 over eta function, eta of it. So this is the Liouville strip partition function with the ZZ boundary condition on both sides of the strip. And then we've got the time-like free boson. Now, for that system, we have an interval with Dirichlet boundary condition on both sides, but they are separated in time. So you have this 1 over eta function as usual, but then due to the separation in time, you get a factor of e to the minus t delta x in Euclidean time. Actually, should write this like so. I think it should be delta x Euclidean squared over 2 pi. I'm working alpha prime equal to 1 unit. So this is similar to a calculation of force between d branes, but now in Euclidean time. So if I'm working in Lorentzian time, then I have to put a factor of I here. So here the delta xe is in separation in Euclidean time. This is the x naught part. So the two instantons are separated by delta x and e in Euclidean time. And finally, we have the BC-Gauss contribution, which will give you eta it to power squared. So this is the BC-Gauss contribution. And it's, of course, perhaps you would have expected this to begin with. The oscillators, which are sum up to these eta functions, they all cancel out. Okay, so the integral is very simple. It's completely elementary. You can do this integral explicitly. The result can be written as 1/2 log of delta x Euclidean squared over delta x Euclidean squared minus 2 pi squared. That's the answer. So if you take the exponentiate twice of this, you just get this factor delta x Euclidean squared over delta x Euclidean squared minus 2 pi squared. Okay, so this is the open string one loop contribution to the instanton measure. That's kind of interesting. It depends on the separation of these two instantons in Euclidean time. Okay, and it's nice that it goes to 1 when they're far separated. So asymptotically, they just look like two separate instantons. Now, if you are going to integrate, over the modular space, you have to take this measure factor into account. But you see that there's a pole. This measure is singular when delta xe is equal to 2 pi. And that's because, or let's say plus minus 2 pi. And that's because when it's separated by 2 pi, what would that be? You call this quote unquote opposition tachyon will become on shell. And that leads to a divergence. So now we're just following our notes here because there is no a priori, no systematic prescription that we know of to how to a priori, consistently integrate over intermodular space. And we have to resolve this singularity of the integral by using an appropriate contour prescription. When we studied this in 2019, we came up with the following prescription. Simply is to integrate in Lorentzian time. And by doing that, we're just going to avoid all the singularities. Okay. You could also imagine some kind of Euclidean contour with some Einstein prescription that superficially could be equivalent to a Lorentzian contour by some rotation, but we worked with the Lorentzian contour in our paper. Let me give you a kind of quick example of how this works in the case of the two instant contribution to the one-to-one amplitude contribution to the one-to-one amplitude at order e to the minus 2 over gs. Okay, so got integral dx1, dx2. There's a symmetry factor because these are identical objects. There are diagrams like this. I show this with the color 1 and 2. Let's say with this closure insertion, omega and omega prime, plus 1 and 2 exchanged. And then we have this instant measure factor e to the 2 annulus. Okay, actually, let me write like so. Oops, sorry about the color. And then there are also contributions of the form, the two disks can end on the same instanton. So let's say twice because they can either on the 1 or 2. So let me say 1. Omega prime. And let's say one of them is incoming, the other one is outgoing. This will also be multiplied by this measure factor. But the second thing actually is divergent when you perform integral, and we have to regularize it by subtracting this by 1. And this can actually be understood as normalized, coming from the fact that we have to normalize the vacuum transition amplitude. So, otherwise you could imagine that vacuum amplitude, you can imagine that the vacuum transition amplitude itself could also receive instant contribution, but you have to divide that out. That turned out to regularize the would-be divergence in the integration of the moduli space. Okay, so this is now, if you follow the Lorentzian contour prescription, and also include the this n factor, which is the normalization factor for the z instant of type 1,1. Let me call this n 1,1. You calculate this, the interval is finite, and you get some nice-looking result that involve, this sinh pi omega functions. But the result does not agree, does not match with the proposal from matrix quantum mechanics. Okay, so for a while we were puzzled by why this doesn't work out. Maybe it's just not the right prescription. But then we recognized that if you assume that there are also contribution from these higher ZZ instantons, then can precisely account for the difference. So unless we include the contribution from this instanton of the type 2,1. Remember, the 2,1 instanton has twice the action of the 1,1 type Z instanton. For the sequence 25 dual theory, there's actually no difference between this 1-point function for 2,1 versus 1,2. But a priori, this could come with a different normalization coefficient, normalization factor for the instant moduli space measure. But it's again a number you can fix once for all by comparing to the matrix model. But there's still something non-trivial to be checked. But because the only ambiguity is the overall normalization, this function here is unambiguous. If you include this, then it works. In fact, not only it works at this level. In fact, due to some combinatorial magic works for n instanton at leading order e to the minus n over gs for all n. You can fix the if you provided that we include or assume that there are contributions of the instantons of n,1 type. But the other types like n 2,2, this will just be 0. This you can just check the answer compared to a matrix model. Because all these contributions are different. They're different functions of the energy. Now, we don't have a deep understanding or physical understanding of why it is the n,1 type that contribute. That's still an open question. But the numerology here is too miraculous to ignore. So we believe this is the correct prescription, but there's still something to be understood. Okay, so let me summarize. Here.
Okay, I have a question. So if I turn on the N2,2, the C equals 1 string theory is still well-defined theory that you do not see any pathology?
Well,
is that right?
it's I don't think we understand it well enough to say that the S matrix is fully consistent because we're just computing the leading order contribution. Now, if you want to understand details about unitary cut and things like that, it's not enough to just work at this order. But by so we are guided by requiring or demanding that this non-periodic completion of sequence one string theory is due to some non-perturbative matrix model. And the only one we can come up with is the sequence one matrix quantum mechanics that I described last time. That's just miraculously work in every calculation that we try to do.
And could this correspond to some deformation that you can do on both sides that you deform away from n 2,2 equals 0?
I highly doubt. So as I mentioned last time, you could. By the way, in retrospect, in view of Ashok Sen's most recent paper, it might be possible to derive these n's from first principle. In fact, I think he has claimed that he has derived n1,1 from first principle, which is in agreement actually with the result we found from the comparing with the matrix model. But independently of that, as I mentioned last time, for example, you could have assumed that all these n's are 0. You could assume that there are no instant contribution at all, and it's not obvious why there's something wrong about S matrix on the string theory side. But it definitely cannot be matched with any analogous matrix model because it will have to come with a matrix model with a fermion reflection phase that doesn't obey the analytic property of the reflection phase of a quantum mechanical system. Okay, so that's some kind of interesting evidence to suggest that you don't want to really the structure somehow is kind of rigid.
So it could be like if I turn on n2,2, then there will be some other branch card or something appear in the complex plan of complex energy plan of the reflection phase, and that we don't want.
That's hard to say because here we're just doing leading order contribution. That reflection phase or the reflection amplitude, this RP, particle reflection amplitude I wrote last time, contains all order answer. Through the NPR formula, it contains all order answer. So, but without that, you cannot really reconstruct the energy structure of this on the complex energy plane for the fermion.
Okay.
Right. Okay, anyway, so let me just conclude on this part. So the conclusion here is that it appears that C equals 1 string theory defined by the worldsheet genus expansion with the Borel summation, together with the instanton effects, appears to be potentially non-perturbatively complete. Of course, we're very far from actually demonstrating this in full because at each instant order, there's still an infinite sequence of perturbative corrections on top of that we only computed that for the one instant case. So there's a lot more to be understood, but at least there's a very strong evidence in my view that this should work out. Note that there is no e to the minus 1 over g string squared effects, and this is presumed because something special about two-dimensional string theory. In higher dimensions, usually you'd expect quantum gravity effects to be of order e to the minus 1 over g string squared, which is absent here. So we just write this down. Effects absent, and also Borel summability of perturbation theory. These are both kind of presumably special to C equals 1 string, and that's not expected to generalize to superstring theory, at least not for the general observables. I haven't really discussed the unitarity of the non-perturbative corrections. So the non-perturbative closed string S matrix does not saturate unitarity. Does not saturate unitarity. I'm not saying that they violate unitarity because who says the closed strings are all the states there is in a theory? And you see, the closed strings are particle hole pairs. If the particle bounces back from the potential and the hole bounces back to the potential, that's scattering a closed string to a closed string. But what about the possibility of having a particle hole pair? Let's say the hole can scatter back, but the particle tunnel through to the left side. So this doesn't look like a closed string state. And this is the reason why this non-perturbative corrected S matrix does not quite saturate unitarity, but that's not a inconsistency. And it would be desirable to understand what these states are in sequence-1 string theory. Now, because this eigenvalue on the left is like a ZZ brane that rolls down from the top of the hill, but it rolls to the wrong side of the tachyon potential. So this is presumably can be described by ZZ brane with open string tachyon rolling to the wrong side of the potential. Now, in open string field theory literature, people have studied in great detail the open string tachyon condensation to the right side of the potential, but to the wrong side, the left side of the potential. This has been explored, but there's a lot of confusion, and as far as I know, there's no clear-cut conclusion about what's really going on there. But somehow that's expected to be these extra states that are only kind of accessible non-perturbatively. Okay, so I think that's all I'm going to say about the non-perturbative aspects. So now for the actual content I meant to discuss in this last lecture, I'm going to return to perturbation theory, but I'm going to consider FZT branes. So the subject for the rest of this lecture will be long strings, the non-singlet so-called matrix quantum mechanics, and the 2D black hole. Okay, so let us recall FZT brane, which I introduced last time. So we've got this Liouville direction with the potential, and the brane looks like this. And it's some distance s away from the strong coupling region. And on the brane, there's an open string that can propagate. This open string can scatter with one another. They can also scatter with closed strings. It's non-trivial dynamics. Last time I discussed that in Liouville theory, with FZT boundary condition on both sides, this will be the open string on the FZT brane of interest. We have these vertex operators. I call them psi p. So for sufficiently large real positive S, I can take P to be a positive real number, and the weight of this open string vertex operator is 1 plus P squared. Sorry, there's this Liouville vertex operator. So the open string vertex operator can be written as up to some normalization e to the plus minus I omega x naught as a boundary operator, this boundary normal ordered, psi P. In this case, I want to take P to be omega because the weight is minus omega squared plus 1 plus P squared, and I want this to be equal to 1. And this to be on shell. Okay, so we can calculate open string amplitudes in the usual way. Like, let's say at tree level, I have 3 point, 4 point, like so. Okay, but this is not as easy to calculate as you might think, because they involve very complicated structure constants of boundary Liouville theory. So for example, this 4 point amplitude or a level of Liouville coordinate function, for instance, can be written as integral dp over the conformal block decomposition. But you have to multiply this by FZT boundary structure constants. Thankfully, thanks to the work of Ponsel and Teschner, all of these structure constants are known. So for example, if you normalize the 2-point function, so generally you can consider two different, S1, S2, two different labels for the FZT brain. So open string stretch between two different FZT brains, and you have states like psi p, S1, S2. So you can normalize two-point function like so with S1 here, S2 here. This, let's say, call it pi times del py minus p2, and factoring out the usual universal spatial dependent factor, coordinate dependent factor. Then, you can talk about, let's say, psi p1, psi p2, psi p3 with some parameter S1, S2, S3. This is some 3-point structure constant, which is actually known, amazingly, that's expressed in terms of contour integrals of ratios of Barnes G functions. They're very, very complicated functions. This one is also known. There's another structure constant you need to know, which is the disk bulk to boundary 2-point function. So this are psi p2 and s here. So this one I call it r s p1 depend on p1 p2. So both of these, so these are known, but they're complicated contour integrals of ratios of Barnes G functions. They are related to the crossing kernel of Virasoro conformal blocks. Okay. I'm not going to write the explicit expression for these because the expression is too lengthy. You can find this in various papers. In fact, the Jiming had nice papers on this subject. Okay, so what is the matrix model dual of SZT brain? Well, this we don't actually know for in complete detail. So there's a proposal by Davide Ghiotto in 2005. The idea is that if you add FZT brain to Tsinghua string theory, the dual matrix model, you should add UN fundamental representation fermions, in addition to these bosonic matrices. I think this proposal is morally correct, but details remains to be clarified. So today I will not be able to tell you the precise dual matrix model dual of the FZT brain. Instead, I'm going to discuss a limit of FZT brain, which we do think that we understand. So instead, we will consider a limit, the so-called long string limit. Okay, so what is this limit? So again, let me draw the picture of the space-time. So the space, here's the alluvial with the potential. And we've got this brain over here. I'm going to take, so this brain terminates at some point. I'm going to take the limit where this parameter S goes to infinity. So the brain recedes to the weak coupling region. Okay, so the brain goes to goes towards large negative phi. Okay, over there, where the brain is sitting at, the string coupling is exponentially suppressed. So the effect of the brain on the closed strings will be negligible. However, if I have an open string on the brain, if I have high enough energy, the open string moves, its ends are stuck on the brain, but the tip can move deep into the bulk if it has enough energy. Okay, so we can consider a very high energy open string in the large S limit that propagates down the FZT brain and comes in and spends some time at the region where the coupling is finite, and then go back out to infinity. So this is the so-called long string. All right, so to be precise, the long string is a open string on the FZT brain, in the limit where S goes to infinity, and the open string energy also goes to infinity, such that omega minus 2s is, I'll define this to be the quote unquote renormalized energy is held finite. Why omega minus 2s? Well, you see, s is going to be, if the brane stretches all the way to the strong coupling region, s is going to be half of the length of the string. So the string has a length 2s. Okay, so in my unit here, omega so the energy due to the tension of the brane, the tension of the open string will be 2s if it stretches all the way deep into the bulk. So this omega minus 2s is a quantity that we want to keep finite. And the expectation is that for these open strings, even if you take the limit s goes to infinity, they're still going to have non-trivial dynamics. And they're going to scatter in a non-trivial way with closed strings and with one another. So Maldacena in 2005 made a conjecture. He says that he proposed that the long strings are due to the so-called non-singlet sector of the matrix quantum mechanics. More precisely, tensor product of adjoint representation of UN sector of the matrix quantum mechanics, which I will define momentarily. Okay, so now we're going to explore the content of this conjecture. Recall in the second lecture I introduced. So in the sequence 1 matrix quantum mechanics, we had this Hamiltonian trace p squared minus x squared over 2, and we got the wave function psi of x, which we chose to write as psi of lambda and omega. Where x is omega inverse lambda omega. But previously, we have assumed the wave function psi to be gauge invariant, UN invariant, so the omega dependence will drop out. But now we're going to slightly relax the UN invariance or singlet condition, invariance of psi, and instead we'll allow psi with let's say to transform to be in some non-trivial representation R of UN. For example, for the adjoint representation, we can consider psi with some index AB, which is of following form: omega IA, omega JB, lowercase psi ij is function of lambda. Okay, so in fact, there's some non-trivial constraint on what this right-hand side psi ij can be, because you have to remember that this thing came from a function of x. It's not just some arbitrary function of lambda and omega. There's a small difference because when you go from x to lambda omega, there's a residual, as we emphasized, this residual Sn semi-direct product with un to the n symmetry. So this un to the n is generated by the left action on omega of e to the I alpha through the e to the I n, I alpha n. This is in the, you can think of this as in the, you can think of this as the Cartan subalgebra or the maximal torus of UN. But I emphasize that this is the left UN action on omega. The gauge rotation on omega is the right action, which is not to be confused with this. Okay, they're slightly different. I mean, the original UN gauge rotation is the right action on omega. Now I'm talking about the left action on omega. Okay. So by construction, the psi is invariant under omega goes to t inverse omega. Because it preserves x. So that actually, in particular, means that this wave function little psi ij here which you can also view this as in the adjoint of UN, but the transform with back to the left UN action, omega, and it has to be invariant under the Cartan. So it lives in the representation, which in this case is the adjoint, but it has to be a zero weight state vector in the adjoint representation. So based on this, I can say that the Hilbert space of the R representation sector of the matrix model can be viewed as it's this space of wave function like this little side here. It's a function of n eigenvalues tensored with the zero weight subspace of the representation of the R representation. So this is the zero weight subspace of the R representation space. And then we have to restrict to the subspace of this that's invariant with back to Sn action. Now, as you recall, if you, depending on whether you multiply the Vandermonde or not, it's either bosonic or fermionic. And it's more convenient to work with the fermion. So last time, in the second lecture, we also wrote that Hamiltonian is this Vandermonde inverse H prime Vandermonde, and we wrote the wave function as Vandermonde inverse psi prime. So this is the fermion wave function. But now it's going to have omega dependence. So let me actually not use the word fermion to avoid confusion for the moment. From now, we're always going to be working with this H prime and this psi prime. As you might recall, H prime, let me just remind you, this is S1/2 partial lambda squared plus V lambda, which is minus lambda squared over 2. And then plus some I not equal to j, Rij, Rji over lambda ij squared. This is factor 1/2. Let me emphasize, I think I might have misspoken in my second lecture. This Rij here is the UN rotation on omega, but it's the left UN rotation. I think I might have said right UN rotation second lecture. It's the left UN rotation, which is the only thing that actually makes sense. So there's this representation space. So for the fixed representation with the left UN rotation, these wave functions actually kind of they're naturally live in subspaces that are invariant under the action of H prime, which is good. Okay, so let's see an example. So let's take R to be adjoint again, and our state schematically, I'll just write it. I'll write this as a wave function in the lambdas. So psi ij, lambda 1 through lambda n. But I will contract this with the state vector in the representation space ij. By the way, maybe I should be a bit explicit. So Rij would act on this by, say, Rij acting on the state KL would just be equal to delta jk il minus delta il kj. That's how Rij acts on this the spaces. And the zero weight condition means that the state, the psi, must be annihilated by R, annihilated by, let's say, RKK for this here, there's no summation, okay, for all K from 1 to n. It follows that only the state II is allowed. So I and j must be equal. Okay, so more generally, we're going to consider the R that is the tensor, so adjoint representation tensor with itself n times. So in this case, the wave function can be written as psi I1 j1 to da, in jn, lambda 1 through lambda n, contrived with I1, J1, in jn. And in this case, the zero weight condition means that the set of indices I1 through in and J1 through Jn are related to each other by permutation. That will guarantee the weight is zero. And furthermore, what would be replacing the fermion statistics is the statement that this wave function is odd with respect to not just exchanging lambda I with lambda j, but simultaneously exchanging I with j on the level of its subscript indices. Okay, so this is a generalized notion of fermion statistics. And as I said, the Hamiltonian on this system is this guy here, which, thanks to this last term, is no longer a free fermion, is no longer non-interacting fermions. So as you can see, the system is all of a sudden a lot more complicated. So this is the system that we're going to study. Any questions so far? All right. The proposal for the dual of long string, this is by Montesina in 2005, is that the long string state, well, I should say that first of all, the theory is interacting. Even if you do perturbation theory, the theory is interacting. So if the long string coming in, it can emit closed strings, can break up and emit a bunch of radiation of closed strings. A long string by itself is not going to be, it's not going to stay, incoming long string is not going to stay outgoing long string. So when we speak of a long string state, you have to be more precise of what we mean. The idea here is that we're going to take the semi-classical limit where the eigenvalue density is high, and we understand that the 1 over the inverse eigenvalue density can be viewed as a coupling constant. And then we can expand the Hamiltonian into quote unquote free part and interaction part. And here I'm going to speak of the long string as an eigenstate with respect to the free part of the Hamiltonian. Okay, so I'll explain what that means explicitly. So the details here are actually quite non-trivial. So the long string state, I'll label it by W, is defined as sum over I, W of lambda I. So as I said, the state has to be contrived with II. And I'm gonna multiply the ground state wave function in the singlet sector. So this is psi naught. This is the singlet sector ground state wave function. Okay, this is this Fermi C that I drew before. That made sense in the singlet sector. I'm just going to take the same wave function, but now I'm going to multiply it by W of lambda I and sum over I. Okay. This is a proposal. Let's try to check whether this can be an eigenstate with back to the quote unquote free part, whatever part of the Hamiltonian that dominates in the large density limit. And we're going to try to determine the function. So here, we're going to refer to this W of lambda as the long string wave function. Okay. All right. So let's try this. Let's take the Hamiltonian H prime and act on the state W. So by definition, you can just look at this. Here's H prime. Let's just plug this in. It's a simple calculation. We can just write this by definition in the following form. So there's some derivative on the W. So we have W double prime lambda I minus W prime lambda I partial by partial lambda I plus the E naught is the singlet sector ground state energy. So this is the singlet sector ground state energy. I don't really care what it is. We'll ignore this for most of our discussion. Times Wi. W of lambda I plus, importantly, there's this interaction term, sum over J not equal to I, W lambda I minus W lambda J over lambda ij squared. Psi naught of these lambdas multiplying the state vector I in the representation space. Okay. Well, this is looks like a mess actually, but we haven't taken any limit. So now let's take the semi-classical, or equivalently the weak coupling limit. So in this limit, we would like to rewrite the sum over eigenvalues into an integration over eigenvalue with eigenvalue density. Okay, so if you stare at this expression long enough, you'll recognize that in fact, the first terms involving W double prime and W prime partial lambda, these terms are subleading in the semi-classical limit. What dominates is the term with the ground state energy, which we'll ignore, and this but mostly this last term, because there's a sum over eigenvalues here, and we're talking about the limit when eigenvalue density is very high. So this last term is actually what dominates. What dominates. And furthermore, to leading order, we can just approximate the eigenvalue density rho by the ground state eigenvalue density. Since we're doing perturbation theory, so the long string eigen wave function equation would be, let's say, I'll call this W E of lambda, where E is the energy, it's going to be the energy of the long string. So the energy of the long string E times W E of lambda is going to be given by this last term here. So we have integral d lambda prime. Remember, the lambda prime ranges from square root of 2 mu to infinity. Recall from second lecture. We have some ground state eigenvalue density rho naught of lambda prime. And then we've got, we just plug in, just rewrite the sum into integral. So we have W E of lambda minus W E of lambda prime over lambda minus lambda prime squared. Okay, so that's a kind of funny looking, eigenfunction equation. It's an integral equation for. So we're looking at integral equation for WE. We can normalize it. Let's adopt a normalization convention. Normalization convention is such that integral d lambda rho naught of lambda WE of lambda WE prime of lambda conjugate is delta function in energy. So the delta function normalized. Okay, so at this point, it'll be useful to actually know what it is, because we're going to use it to compute scattering amplitudes. I'm trying to think how much detail I want to explain on this. Let me say the following. I just want to give you all the recipe that is required to actually solve for WE of lambda. Okay, so first of all, the first thing one observes is actually, it turns out that the energy E is divergent. This is an infrared divergence due to the kind of weak coupling region, or the region of large eigenvalue where there's no actual dynamics. So we have to put in an IR cutoff on tau. Remember, tau is a spatial coordinate related to lambda by this relation, lambda is square root of 2 mu cosh of tau. And by the way, the rho naught is 1 over pi, square root of lambda square minus 2 mu, as I wrote before. So we're going to define the renormalized energy of the long string. Epsilon to be E minus L over pi. It turns out that there's some finite constant that you can fix so that this epsilon will have some nice property. so far, you can view this as a definition. This is a quantity that will be finite. This -1, so far, you can just view this as a convention. So the wave function, W of alpha, of lambda, turns out that we can write in the following form, H epsilon of as function of tau over square root of pi rho naught of lambda. I guess I'm using a tau and lambda interchangeably. There's some nice way to rewrite this equation. I think I will not really get into the details of that. I will just say that this H epsilon of tau is a function that one can write down explicitly. So this was solved brilliantly by Witkowski in 2005, shortly after Huang's paper. The solution for this is important for our purpose, but it's not particularly illuminating to write it down. Maybe I should write it down just so you can see how complicated it looks like. So let me write this down. So H epsilon of tau is integral dk over square root 2 pi minus infinity to infinity sine of k tau sinh pi k over square root of sinh squared pi k plus e to the 2 pi epsilon times sine of pi is go from k0 to k dk prime sinh pi k prime. So there's some really bizarre looking functions here. And k naught here is I over pi arc sine e to the pi epsilon. Okay, so this is a completely bizarre looking function that you would never have guessed, but that's the answer. That's the solution to this long string wave function against the equation. And believe me, we're gonna match this with something from the worldsheet. Okay, so that is going to be the miracle. All right, so now we're gonna consider scattering of long strings. So you may wonder whether the long strings really have well-defined scattering amplitudes because they're infinitely long objects. However, most of the region where the long string occupies, the coupling is exponentially suppressed. So really only the finite part of the long string is effectively interacting. So that suggests that long strings should have well-defined scattering amplitudes. In practice, it's not obvious from the worksheet, in fact, directly in the worksheet computation that the scattering amplitudes of long strings are well-defined. For example, if you study long to long, so the scattering of a pair of long strings, or for example, a long string can split into a long string and a closed string. So this corresponds to at tree level worksheet diagrams that look like this. So remember, these long strings are open strings in the high energy limit on the FZT brane. This one, second diagram will be something like this. If you actually calculate this diagram, they're very complicated because they involve all these FZT boundary structure constants. And then you take the limit where S goes to infinity, open string energy go to infinity simultaneously. And you have to show that these amplitudes are finite in that limit. I actually do not know a direct CFT argument why that's finite, but we checked this numerically and it works in some miraculous way. Okay, so the claim is that from the worksheet point of view, at least numerically, we can verify that the long string limit, these long string scattering amplitudes are actually finite. And we can calculate numerically. Now, this numerics is a exercise in integrating conformal blocks once again. So it's a matter of computer numerics, which we did, but I won't discuss in the lecture here. I'm just going to discuss the matrix model side of the computation, which is simpler, but it took us much longer to get because it's actually quite subtle. So the matrix quantum mechanics. Okay, let me say that. So worldsheet is tedious but straightforward numerics, but it can be done. Okay, so now I'm going to explain the matrix quantum mechanics computation. Okay, so let me start with this long, long going to long, long, which is actually slightly simpler. So they are, from the worksheet point of view, there are two possible kind of diagrams, disk diagrams. You can have in, out, out in this alternating order, or you can have in, and out, out, like this. It turns out the second diagram goes to 0 in the long string limit, and the first one is finite. This can be understood actually quite intuitively because let's imagine that you have two FZT branes. You have 1 and you have 2, and the long strings are, there's one that's that ends started on 1 and ends on 1. Let's say there's another one that starts on 2 and ends on 2. Let me draw these slightly differently. Different length, like this. Okay, so now you can consider a recombination process in which I have, so the branes are still here, but the strings, the long strings reconnect into, let's say, like that, and like that. Okay, so so now these the point is that this recombination process, this is a tree level process, but this recombination process can occur in a finite coupling region. So that's why this thing survives. This other second diagram, this other diagram would require the recombination to happen at the end of the string, which is all the way in the weak coupling region. That's why that diagram does not contribute in this limit. So it makes sense. But from the matrix model point of view, the basis states can look like this: ij, ji, or ii, jj, and the scattering process will have to exchange these two. Okay, so let's say, so here I think of the index I as ending on the first FZT brane, the j is on the second. So I call this the 1221 type, and this one the 1122 type. So for example, I can consider a long string state with the two long strings, WE1, WE2, of the 1122 type. If I write down the wave function explicitly, it is sum over ij, WE1 of lambda I, WE2 of lambda j, the ground state singlet sector wave function, psi naught lambda 1 to lambda n, and ii, jj. Likewise, so similarly for this thing with 1, 2, 2, 1. So now I can calculate the tree level long to long scattering amplitude in the matrix model using the Born approximation, similar to this example I showed in the collective field theory. So this is minus 2 pi I. The WE3, WE4, let's say in the sector 1, 2, 2, 1, the interaction Hamiltonian, H prime interaction, WE1, WE2 in the 1, 1, 2, 2 sector, where here the only relevant part of the interaction is this 1/2 sum over I not equal to j, Rij, Rji over lambda ij squared, minus the long string energy itself, E1 plus E2. I mean the free part of long string energy, because I'm looking at the sort of interaction part. And of course, energy will be conserved here. So we can do this calculation semi-classically, where everything is in a semi-classical approximation here. By the way, all of this calculation of long string I'm describing so far is at tree level. We do not yet know a systematic way to do this at loop order. But the tree level is already sufficient and trivial. So this is 2 pi I. You can turn the sum over I and j into integral. So you have integral over d lambda prime. We just plug in the ground state eigenvalue density rho naught of lambda rho naught of lambda prime, and then we'll plug in the wave function, which is WE3 of lambda bar, WE4 of lambda bar, and WE1 of lambda minus WE1 lambda prime. Recall it's the same kind of factor that appears when Rij acts on the wave function, as I showed in the earlier example of the single long string case. Over lambda minus lambda prime squared. Okay, this turns out to be a well-defined integral. You can just integrate this numerically. You have to integrate this numerically using a long string wave function. Remember, the long string wave function was this horrendous mess that was solved by Witkowski in 2005. So we just plug this in numerically and calculate this integral. And by some complete miracle, the result matches numerically with the long string limit of this world sheet diagram, where we have in, out, out. Okay, so this is truly a miracle, because the world sheet computation, not only is it a completely different computation, it involves integrating conformal blocks against these horrendously complicated FZT boundary structure constants, which are, the formulas that appear in the crossing kernel of your Sorel conformal blocks. On the matrix model side, you have these horrendous functions which have nothing to do with this, and yet the result agree to high accuracy numerically. Okay, so that somehow, is, to me, is extraordinarily convincing evidence that things work out. But we can also do this computation for the tree level long to long plus closed, which is similar, but it utilizes some more aspects of this interaction Hamiltonian. So maybe it's worth explaining this, just because it actually is sensitive to some other interesting feature of this matrix model Hamiltonian. So this, again, by Born approximation, is minus 2 pi I W E2 W E1 here. So this is E1 going to E2 and omega 3. Omega 3 is the energy of this closed string mode, which you can put here as a annihilation operator, omega 3. And here I insert the interaction Hamiltonian. So this is the Born approximation calculation for this amplitude. So now I just need to calculate this and compute the overlap. So this I already know. I've written this down before. But the key is that we have to rewrite this in a way that's expressed in terms of the collective field, because this A is a mode. Remember, this is the mode of the collective field. Okay, so that's the tricky point. So H interaction acting on the long string wave function, as I already explained earlier, is given by this expression involving some WE1 double prime of lambda, is WE1 prime lambda partial lambda I, plus another sum, but now I can turn the other sum into integral. And the relevant part of the integral is going to involve the fluctuation of eigenvalue density, which is now partial lambda 1 over square root pi, as you might remember, partial lambda of eta lambda. This is how we define the collective field, as the derivative of the collective field with vector lambda is the fluctuation of the eigenvalue density, then multiplied by WE1 lambda I minus WE1 of lambda over lambda I minus lambda squared. Then times the ground state wave function of the singlet sector times I summed over I. Okay, so okay, so if you compute this in the semi-classical limit at leading order, compute this overlap, it will turn out that if you inspect this expression carefully, it'll turn out that it is the first term actually doesn't contribute at that order. It scales differently with mu. So it's the second term and this last term that will contribute. So the second term here, this W prime of lambda term, give rise to, this involves a derivative with that eigenvalue. And this gives rise to something that's proportional to the canonical momentum conjugate to the collective field. So you get something like integral lambda. So again, you turn the sum into integral now, psi naught a omega 3, this pi lambda, which I defined in the second lecture, then WE2 lambda bar partial lambda WE1 lambda. I guess let me just write this WE1 prime. With some factor they can keep track of. And the second term gives rise to something that looks like the following. Rho naught of lambda, psi naught a omega 3 partial lambda prime eta of lambda prime psi naught times WE2 of lambda bar WE1 of lambda minus WE1 of lambda prime over lambda minus lambda prime squared. So with the expression like this, and now it's straightforward to use the mode expansion of eta and pi as conjugate momentum. For example, as you recall, from second lecture, eta of tau is, can write as integral dp over square pi 1 over p of AP plus AP dagger times sine p tau. Okay, so that was useful here. That's why I bothered to introduce that or that formalism, where AP and AP prime, remember this commutation relation is like this. That's how we normalize the gradation annulation operator. So now everything is straightforward. You can just plug in into the integral. And the result, once again, agrees by some miracle numerically with the long string limit of this open, closed, open amplitude. Okay, so this is just to explain how this computation is done on the matrix model. I cannot really show you the numerical details on the string theory sides, but it works out with the they turn out to agree to high numerical precision. Any questions about this?
Do you also have a NPR-like prescription for?
No, we don't. No, we don't. So that's to me is a major open question. It would be nice to understand how to do that. Not only we don't understand number, so NPR's prescription is non-perturbative. We don't even understand how to go beyond this order in perturbation theory in a systematic way. So yeah, it would be nice to understand that.
And you also said that the collective field prescription will only work for tree level, and
that's right. The collective field is at least it's not obvious how to extend it to loop order. First of all, the theory is formally not renormalizable, so we have to regularize various divergences, and it's not clear how to deal with that because there's no a priori reason why this collective field theory should be valid in the first place, because it's derived by this Fermi droplet picture, which is only valid semi-classically. Mm-hmm. Right. Okay. So that's indeed a important open question here. Without that, we cannot really extend this computation to higher loop order. Mm-hmm. Okay, but to me, this computation was done in our 2018 paper, and to me, this was a extraordinarily non-trivial evidence that suggests this proposal is really correct. Because it's just there's no way that it could be wrong because of how non-trivial these agreements are. Having established that, we want to explore some consequences of this long string dynamics. So in the final part of my lecture, I want to talk about some aspects of sequence-1 string at finite temperature. This is going to be, we're going to come back to long string momentarily. But first, let me say that at finite temperature, even without long string, the closing sector still makes sense and is actually non-trivial. In fact, we can talk about non-trivial observables such as a notion of thermal S matrix. Now, normally in a quantum field theory, at finite temperature, you don't expect to have a well-defined S matrix because the idea of asymptotic states may not make sense at finite temperature if you have a thermal bath. But the C=1 string theory is a little special because the asymptotic region, the coupling constant dies off exponentially. So even if you turn on a thermal bath, you would imagine that in the asymptotic region, the asymptotic particles does not interact with the thermal bath. So you can define potentially a finite temperature S matrix. Okay, so in fact, I think it can indeed be defined. I'll call this S as some temperature T. And this formally can be viewed as a trace of some thermal density matrix of some out annihilation operator for the out particles and some in creation operator for the created in particles. As I said, this is supposed to make sense when the effective coupling dies off sufficiently fast in the asymptotic region, which is the case here. Now, can you compute such things? As usual, from the string theory point of view, you would expect that if you continue x0 to Euclidean, you're talking about Euclidean target space where the Euclidean time is identified by periodicity 2 pi r, where 2 pi r is equal to the inverse temperature. Both from the point of view, this you can kind of try to use this trick both from the point of view of the matrix model and from the string theory side. And you can try to get scattering amplitudes by analytic continuation of the modes. So the energy, of course, would be the Lorentzian energy would be the energy that is real in the Lorentzian signature would not respect the quantization condition with respect to this Euclidean circle. Instead, what you want to consider this so-called Mitsubara frequencies. So the energy would be, let's say, I n over r, where n is some integer. So for instance, on the string theory side, you might try to do a computation with n continued energy, which is I n over the radius r. And then if you have the answer, somehow you try to continue back to Lorentzian signature. That would be the only known prescription that I can think of. In the matrix model side, you can actually apply the NPR prescription to this. So remember, for example, I'll just give you an example, one-to-one amplitude as a function of omega of the incoming or outgoing particle energy. This was integral dx of the particle amplitude, reflection amplitude, with its arguments multiplied by the whole reflection amplitude. So in the thermal case, we can generalize this to a one-to-one, the thermal S-matrix elements with omega equals In over R. This integral will now turn to a discrete sum. Remember, this X is the kind of the particle or whole energy, which is now discrete and imaginary. So minus I over R, sum n from 0 to n minus 1. So n is like the total energy now, times Rp of, my computer is making some noise. Let me close something. Hopefully it's not as noisy. Rp of minus mu plus omega minus I m plus 1/2 over R. This is because the Kavli model is a boson. The base periodicity boundary is periodic along the thermal circle, but the fermion has to be anti-periodic. So that's why there's a 1/2 shift here, times RH minus mu minus I m plus 1/2 over R. I'm not sure why my computer is making noise. One moment. Okay, not sure why. Anyway, is my audio okay?
It's okay. It's not very noisy.
Okay. So yeah, this is because of the fermion anti-periodicity. Okay, and you can actually do the sum, and you'll find that at tree level, the result is not modified, and that's always the case at finite temperature. But at one loop, there's a correction that looks like some polynomial of omega again, and the correction is here, 1 over r squared. So it's some simple correction, but nonetheless, it's non-trivial. This is some kind of thermal correction to the one loop one-to-one amplitude. Okay, so there's some content to the dynamics of finite temperature. So you can ask, can you reproduce from the worldsheet? You have to repeat our calculation of the torus, 2-point amplitude with maybe omega equals in over r, and this omega prime, so minus in prime over r, with with a compact boson, with the xe is now compact boson. So we haven't done this computation. We hope to do this at some point, but we haven't done this computation. And it'll be very non-trivial to reproduce this at genus 1. Any questions about this? Finally, I'm going to discuss a decoupling limit of the FZT branes. This is the thing that's going to make some connection with black holes. Let's consider the Liouville spatial direction again with this potential. And we've got some FZT brane that's sitting over here. I'm going to take this S parameter again to be large. But now, instead of saying the FZT brane just disappears into weak coupling region, I'm going to put a large number of them. So the total number, I call it NF. And this distance, again, this is S. So I'm going to consider the limit where NF goes to infinity and S goes to infinity at the same time, so that the FZT branes disappear in the sense that they retreat to the weak coupling region, so there are no open strings around. But if I have enough of them to compensate for the weak coupling, then their influence on the string, on the closed string, would still so influence on closed strings remains. So one can imagine defining such a decoupling limit. So this will lead to some kind of deformed closed string background. Okay, so it turns out that this nice limit can only, as far as we understand, can only be obtained if you work at finite temperature, for the reasons that I'll explain shortly. But for now, let's just entertain the possibility of considering this decoupling limit at finite temperature. So let's consider finite temperature is 1 over 2 pi r. Okay, so and let's consider some, let's say, some generic closed string scattering amplitude on the worldsheet. Now the effect of the FZT brane is that it's going to cut some holes on the worldsheet. Well, I guess this is supposed to be a hole, so let's say over here. Okay, so at each hole, so the worldsheet is the remaining stuff, all that stuff. At the hole, I have this boundary condition of the FZ type with the Champ-Hayden factor, UNF. Okay, so at the hole, we're supposed to insert a boundary state, FZT, with the parameter S. Let me remind you what this boundary state looks like. It looks like integral 0 to infinity dp over pi of this 1-point function psi s FZT depends on Liouville momentum P, Vp Ishibashi state. And this one-point function is some numerical factor times cosine of 4 pi sp over sinh 2 pi p. Actually, let me be a little more precise. This thing here is the FZT boundary state tensored with the Neumann boundary state. Let me just write, yeah, okay, I'll write double head notation in the X0, the time-like boson sector. There's also the ghost stuff, which is standard. Okay. But now have to remember that but now I have replaced this by this by X0 by the Euclidean time, which is periodic. It's a compact boson, and the Neumann boundary condition in the compact boson CFT source is 1D modes. Right, this thing sources 1D modes. There's a quote unquote 1D mode. It's 1D mode in Euclidean time, whatever that means. Okay. All right. So now in this decoupling limit, in this this some kind of 't limit, in this decoupling limit, our expectation is that the FZ branes themselves disappear, but their influence remains, and the influence is through the closed strings sourced by the FZD brane. So you might naively expect that what happens here is that a priori you have to integrate over the moduli space of these Riemann surface with all these holes, which is quite complicated. But in the limit of interest, each of these holes should kind of shrink. And you just have the closed string sourced by the FZD brane that's approximately on shell that enters this worldsheet diagram. So I don't actually have as of now, a completely rigorous CFT argument. But if you believe this picture, then you can read off the contribution, the relevant closed string contribution, which comes with a factor. So each hole has a factor of G string, has a factor of NF from the Champlain factor, and it has this integration with the Liouville momentum, dp over pi, the one-point function. And then it has a sum over winding states, winding number W over integer. And for each primary winding state, there's a propagator. When you integrate over the moduli, it gives rise to a propagator 1 over p squared plus the mass squared, which is W squared R squared over 4. And then the winding vertex operator, which is e to the I WR, x left minus x right. This is the left and right moving part of the Euclidean time free boson times the Liouville vertex operator, plus descendants. Also, things that involve oscillators. So the conjecture here is that, the conjecture here is that in the S goes to infinity limit, in the decoupling limit, when I send S to infinity, we should pick up the dominant term in this contribution. And so let's inspect that. Now, if you look at this integral naively, it actually is divergent. So there's a singularity at p equals 0. We have to kind of regularize the integral to avoid p equals 0. We can do this in the following way. So remember that this disk one-point function is this function here. So here, I'm going to make a proposal. This is not yet rigorously justified, but it seems to be reasonable. I can double the integral over p to the entire real line on the complex p plane. So this is a complex p plane. So originally, the contour is along this real axis, but there's a singularity at pico 0. So I'm going to deform the contour into either the one above, let me call this one C plus, or the one below, let me call this one C minus. So so we're going to split. Okay, let me right here. So this psi S FZT P, which is proportional to cosine of 4 pi S P over sinh 2 pi P. We can rewrite this as e to the 4 pi I S P plus e to the minus 4 pi I S P. We're going to integrate this one along the contour C plus and integrate this one along contour C minus. And then we can deform each contour. We can push the C plus contour to the upper half plane and C minus contour to the lower half plane and pick up a contribution from the residue. So in the large S limit, it's going to be dominated by the first residue it encounters, the first pole it encounters. And first pole it encounters would be at IR over 2 and minus IR over 2, provided, so if R is less than some critical radius, which is equal to 2, the leading contribution in the S goes to infinity limit is given by the residue at P equals plus minus I R over 2. And if you look at what that gives you from this operator here, it gives you G string times NF e to the minus 2 pi SR over R sine of pi R times the winding operator cosine of R x minus x right times V. But now it's a VP and continued, right? Because we're deforming the contour, pick out the residue as imaginary P. So this P is equal to IR over 2. Okay. Now that's okay. So this part of the argument is a bit heuristic because it's not completely rigorous. I do not have a completely rigorous justification that all the corrections will be suppressed, but it seems to be reasonable. And the result, this conclusion seems to be also reasonable. So the claim is that this coefficient, this is the thing you want to keep finite. So let's call this lambda. This is some kind of 't coupling. Quote unquote 't coupling in this story. And what is this? This vertex operator. This is known as the T-dual of sine Liouville deformation. By construction here is marginal. Okay, so we start with the Liouville theory times a compi boson in Euclidean time, but then we're deforming that background by this T-dual of sine Liouville coupling, which involves a winding mode. This thing still grows still grows in the strong coupling region and dies off in the weak coupling region when R is less than R critical. By the way, this is why we need to work at finite temperature, because this condition will not be satisfied if R is bigger than R critical, which corresponds to the low temperature phase. So the claim here is that if you're above this critical temperature, then the decoupling limit leads to this deformed background of C equals 1 string theory. Okay, so what is this deformed background? Well, we start with the compi boson, this X Euclidean, and Liouville direction phi, like this. That's the topology of the cylinder. And this Liouville potential V of phi, like this. We are deforming this by adding to it deforming by winding modes of one number plus minus 1. So what does it do? Well, at least heuristically, your expectation might be that if you deform by the winding mode, then one number is no longer conserved. So geometrically, if the topology is a cylinder, one number will always be conserved. So the only way for the deformation to destroy one number conservation is if the cylinder caps off. It looks like a cigar. Okay, so this cigar is not the same as what's commonly known as cigar in string theory literature, which refers to a special case. So if the deformation parameter lambda, so if lambda goes to infinity, then the Liouville part becomes negligible. We just have the T dual of sine Liouville. And there's a special radius where if R, or let's say, when R is equal to a special value, turn out to be 3/2, this T dual sine Liouville is equivalent to the SL2 mod U1 coset CFT at level k equals 9/4. This is the usual cigar. This is the Witten's 2D black hole. But that cigar, which is an exactly solvable model, simply sits as one point in a family of theories, which is much more general. And my guess is that this T dual sine Liouville is a thing that should correspond to a general 2D black hole, and which contains some special integral points, but that seems to be not very important for this discussion here. Okay, so let me summarize. The conclusion is that the decoupling limit of FZTT at finite temperature leads to some thermal background of the closed string theory, interpolating between the vacuum and this T dual of sine Liouville, which is what I call the black hole, the Euclidean black hole. So this is finite temperature. This is above some critical temperature. Okay. So in principle, you can try to study worldsheet observables, some analog maybe of string S matrix, using conformal perturbation theory on the worldsheets, perhaps. But it seems to be technically quite difficult. You can at least try to do it perturbing in lambda, but even that is quite difficult. But it's something that's definitely worth doing. So maybe at least perturbation theory in lambda, maybe this can be done. And the interesting question is, what is this due to? Even though, as I said, we do not yet know the precise dual of the SDT brain, the matrix model, we don't actually need it because this is similar to a long string limit. So the natural conjecture is that this should be due to a thermal bath of long string states, which I have already described to you in some detail in the non-singlet matrix quantum mechanics. Well, that's the question. And this is not yet established on solid footing, I would say. I gave a heuristic argument that suggests why this should be true. But I think one should not really be fully convinced until there's some more concrete evidence. There's some current work in progress in which we hope to match some non-trivial observables, such as perturbative correction to the free energy in lambda. It hasn't worked yet, but trying to track down, maybe we made some mistake. So the status of that is not yet clear, but I think this conjecture is very suggestive, and it's very likely to be correct. And we should investigate the details. So I'll finish here.
Okay, let's thank Steve for a very nice lecture and the sequence of 4 lectures. Any question for C? So about this lambda parameter, so how do I know that this will give me an exactly marginal deformation?
So this operator is marginal, and it's not normalizable. I think if you, I think it's essentially marginal. Should be exactly marginal for the same reason that sine Liouville is exactly marginal. I think if you study the OPE with itself, it will not give rise to, for example, additional. There will be no beta function. It will not give rise to other margin operator in this OPE. But this is a bit subtle because the operator is not normalizable. You have to be careful in how to do conformal perturbation theory.
That's right, but you also have the original Liouville.
That's correct. That's correct.
So you need to consider OP of these two.
Yeah. That's correct. But in this case, typically in the situation where we have this exponentially growing operator, it tends to be the marginal things tend to be exactly marginal just because formally, when you take the OP of these things, you don't actually produce other marginal operators in the OP. You produce some higher exponentials.
Mm-hmm.
It's not really established on rigorous footing, but I'm not aware of any evidence against the claim that there's actually this one parameter family of CFTs interpolating between Liouville and sine Liouville. I mean, sorry, Liouville times Fourier boson and sine Liouville.
Okay.
Maybe I should mention one subtlety, which is kind of an important subtlety, because people often say that sometimes people say that the 2D black hole, you cannot change the temperature. You cannot deform the radius of the cigar. It is true that in the nonlinear sigma model description of the cigar, if you solve the, so you have some non-trivial metric and you have some non-trivial dilettante profile turned on, and you just try to satisfy the beta function vanishing condition and solve for smooth solution, you will not be able to deform the asymptotic radius. So that seems to be in conflict with what I'm saying here. But the claim is that that's only true in the semi-classical limit when the cigar radius is large. But here the cigar radius is not large. The cigar radius is below this critical value. So I think in this regime, you cannot trust the nonlinear sigma model description in the weak coupled nonlinear sigma model description. And in fact, from the sine Liouville or the T2 sine Liouville point of view, there's no reason why you should not be able to deform the radius. But on the other hand, it also suggests that maybe it's in some kind of qualitative way different from the low temperature phase. There's some debate about whether this thing should really be viewed as a black hole. But so far, one can discuss whether it really is a black hole, but there's a sense in which it looks like a black hole because it has these, because the one number is not conserved, in the setup.
Okay.
Can you supersymmetrize the Liouville model?
Can I what?
Supersymmetrize.
Supersymmetrize. I guess in the abstracts of the lectures, I mentioned that I would talk about type 0 if I had time, but I don't have time. There's a well-known, maybe I'll just say it very briefly. There's a well-known extension of this duality, which is the type 0 B and also type 0A. I'll just focus on type 0B for now. On the worksheet, it involves n equals 1 Liouville together with some x naught and psi naught. Similar to the worksheet theory of NHR formalism of superstring, but you do a diagonal GSO projection. And so you're going to retain only NS and RR states. So it's a theory with worldsheet supersymmetry but space-time is just bosons. Again, in 2D target space in a similar way. And the dual of this, so let's ignore the 0A. The dual of this is a conjecture to be this two-sided same matrix Hamiltonian, but you fill both sides of the Fermi sea. So this is a very beautiful conjecture, but the evidence for this are actually fairly limited. Actually, in some ongoing work with that I'm doing with Bruno and Victor, we are studying this version of the duality, which extends the C+1 story. We have some preliminary evidence that the Dinstan effects, in the string theory side agrees with the matrix model side. So here, actually, there are both d-instantons and anti-d-instantons. They correspond to eigenvalues tunneling to the left or to the right. And we can do worksheet computation with d-instantons and anti-instantons, and there's some agreement. But actually, this conjecture duality has not even been checked at tree level 4-point amplitude. So we're actually going back to check the tree level 4-point amplitude at the moment. That requires some new work to, one has to implement this recursion relation for the n equals 1 super Virasoro conformal blocks, which has been, so far successfully implemented. And we're at the point of actually compute this numerical integral over the moduli space to get hopefully the correct sphere 4-point function, 4-point amplitude to match with the matrix model. If we can get that to agree, I think we'll publish the paper. But so far we're still doing that.
All right, thank you.
Yeah.
There's a question.
The question asks, can I think of the SD brain as some end of the world brain? I don't think so. I mean, this is just some kind of half space filling brain, nothing more than that. Yeah, it's some. I don't know what to say other than saying that it kind of fills a part of the space. But I should emphasize that two things. So first of all, this brain, because it extends all the way to infinity to asymptotic region, it changes the asymptotics. That's why you cannot think of the brain as an object in the same matrix model. Okay, so this, if you have equal FZ brain, you have to think of this as an extension of the matrix model. So indeed, in Davide Ghiotto's proposal in 2005, he proposed that you have to add some additional fundamental matter to the matrix model. So I think that proposal is morally correct, but it will be very nice to actually demonstrate how it works exactly. So far, that proposal has not even been understood at the level of kind of just recovering the open string spectrum. We tried at some point a few years ago, try to, make sense of that, try to match, open string scattering amplitudes to this matrix model with fundamental matter. We have not been successful, but this is one of the outstanding open problems on the subject.